Balancers. Do you ever wonder how they came up with them? To all of you who will be starting your Factorio journey, hello. My name is Manimo, and this short video will provide a mathematical analysis of the construction and effectiveness of balancers. You will be able to construct your own balancers of any size you want at the end of this video. The following is a joint work with Bitfoot and Colby Reynolds. Section 1.1 Preliminaries. Before we begin, let us define what we mean by a balancer. Consider a construction that takes n belts of items and outputs m belts of items. We associate the following variables to these belts: yj, s, and xi, t. These are variables indicating the content of the belt, with the subscripts indicating the specific belts and the superscript indicating the left or right hand side of this belt. We will let these variables to take values in the vector space QSItem, where it's freely generated by the basis SItem, which is the set of items in Factorio. We may sometimes omit the superscript in situations that are insensitive to lane size. More precisely, we can set yj to be the sum of yj left and yj right, and xi to be the sum of xi left and xi right. We further combine these variables into vectors, which can be used later. Definition 1.1. A balancer is a construction of belts that takes items from n belts and outputs items onto m belts. A belt balancer is a balancer that takes in xi items on the ith belt and outputs yj items on the jth belt. A lane balancer is a balancer that takes xis items on the s side of the ith belt and outputs yjt items on the t side of the jth belt. We also say a balancer is output balanced, respectively lane output balanced, if it splits the overall sum of all input belts into m, respectively 2m, pieces, and put them onto each of the output belts, i.e. yi is equal to yj for all I and j. A balancer is input balanced, respectively lane input balanced, if it takes the same amount of items from the n or respectively 2n inputs and put onto the output belts, i.e. xi is equal to xj, or respectively xis is equal to xjt. Example 1.2. Here are some examples of various types of balancers. 1. When outputting from a train to a certain storage, one often needs an input balanced belt balancer so that each wagon of the train unloads at the same time. You don't want some items to be still remaining in the wagon when the other wagons are empty, thus delaying the train. 2. When splitting a bus into multiple copies of a factory, one often needs an output balanced belt balancer so that each factory receives the same amount of items. 3. When putting ore into a furnace array, one often needs an input balanced lane balancer so that the miners on both sides of the belts extract the same amount of ore. Because otherwise, if at some point one consumes less than half a belt of ore, then mines on one side may run out first, and later this person can only have half belt of ores when the higher consumption is required. 4. When extracting fruits from gelba, one often needs an input balanced lane balancer, so that one lane does not spoil before the other lane. An important feature of the balancers of interest for us is throughput. This is motivated by the idea of planned input flow and realized input flow. For instance, one may construct 4 input belts and only 1 output belt, in which case even if one plans to input 4 belts of item, only 1 belt of item can come out of the system due to the outward flow limit. We're mainly interested in balancers where all input will be consumed, i.e. the sum of all yj's is equal to the sum of all xi's. This is called a conserved flow. This prevents, for instance, a balancer that has 8 input and 8 output belts, but is only capable of outputting 7 belts of items due to undesirable design, or maybe low consumptions downstream. Remark 1.3. Note that the notion of input balancing is mainly relevant when flow is not conserved. That is, when the planned input flow is bigger than the allowed output, causing the realized input flow to be lower. In that case, we should really add additional variables to indicate the realized flow of the input belt, which necessarily sum up to the total realized output. Section 1.2 Splitters. Splitters are the simplest balancer. Before we introduce them, let us list some assumptions. Assumption 1.4. As mentioned in the previous section, we assume a few properties for our balancers of interest. For the following sections, unless otherwise specified, we assume the following. 1. A balancer is an output-balanced belt balancer with conserved flow. 2. A balancer consists of exclusively belts, splitters, and underground belts. In particular, it does not contain any inserters, chests, or loaders. 3. A balancer is time-independent, i.e., its behavior remains consistent as time and item pass through the system. In particular, the balancer is not controlled by circuits that change behavior depending on time. 4. A balancer does not have intersecting belts, i.e., all mergings of belts are done by a splitter, and not by side loading. Under these assumptions, let us analyze the behavior of a splitter. The splitter itself is a balancer. It can take up to 2 input belts and output up to 2 belts. Here are all the possible setups with a single splitter without side priority or filters. Let us observe that the input and output of these 4 splitter setups can be described by these matrix equations. Note that case 3 does not have conserved flow. Section 1.3 Matrix representation of a balancer. Suppose we begin with n parallel belts and put a splitter between the ith and the i+1th belt. Then we obtain the balancer, defined by the operation of the following matrix. Note that we have replaced the ith and i+1th row and columns with 1/2. We can similarly balance 2 arbitrary belts. Definition 1.5. An elementary balancer is a balancer with a single splitter on the ijth belt for some ij. More generally, consider a balancer of n inputs and n outputs, composed of a chain of elementary balancers E1 up to En. This build is then split into n steps, where the ith step uses the splitter Ei to mix the Si and Tith belt. By abusing the notation, we would also denote the corresponding matrices by E1 up to En. The output of this balancer is then exactly computed as follows. Y is equal to En times En minus 1 times all the way down to E1 applied to X. This motivates the following definition. Definition 1.6. A balancer is a linear balancer if it consists of a chain of elementary balancers with no filters and side priorities. The associated matrix of this balancer is the unique matrix S inside the matrix space such that Y is equal to S times X. When the output of a balancer S1 can be matched with the input of another balancer S2, we may compose them and obtain a combined balancer S. Its associated matrix is simply given by S equal to S2 times S1. Example 1.7. Consider the following balancer. It is the composition of the following 4 elementary balancers E12, E34, E23, and E14. Its matrix is given by their product, which is filled with 1/4. Note that this means that the balancer is output balanced. This in fact is the common 4-lane balancer. Section 1.4. An analysis of 2 to the n lane balancers. It is obvious that to balance 2 lanes of belts, we need 1 and only 1 splitter. We have seen previously that 4 splitters can be used to achieve a 4-lane balancer. A natural generalization of this is to balance 2 to the n belts of inputs and outputs. Question 1.8. What is the minimum number of splitters? required to construct a linear balancer with 2 to the n belts of input and output. The following is the complete solution to the above question. Theorem 1.9. Let capital N be 2 to the n, and let Sn be the capital N by capital N matrix filled with 1 over capital N, which represents an output-balanced 2 to the n belt balancer. For I and j distinct, let Eij denote the capital N by capital N elementary balancer between the I and j's belt. Then we can conclude the matrix Sn can be written as a product of exactly n times 2 to the n minus 1 matrices of the form Eij, and this representation is minimal, in the sense that if Sn is equal to Eikjk, Eik minus 1 jk minus 1, all the way down to Ei1 j1, then we necessarily have k greater than or equal to n times 2 to the n minus 1. Let us prove this theorem. For easier manipulation, we shall index the rows and columns by binary coordinates, x equal to x1 up to xn, where each entry is an element of z mod 2z. This way there are capital N equal to 2 to the n indices in total. For any t inside the set from 1 to n, we set et to be the binary string that has a 1 in the t's position and 0 elsewhere. We shall also denote ex for binary index x to be the vector with 1 in the x position and 0 elsewhere. Let us define some matrices, At to be equal to the product over all binary coordinates x such that xt is equal to 0 of the matrices ex x plus et, where the summation here represents coordinate-wise addition. This product represents a balancer that balances a belt with another belt that is 2 to the t minus 1 away from it. For instance, if n is equal to 4, then A1 would be balancing belts 1, 2, and 3, 4, while A2 would be balancing 1, 3, and 2, 4. Combining A1 and A2 gives us a proper balancer. Note that in this construction we never used any splitter between the belts 1, 4, and 2, 3, and the rest of the proof will show us why missing these splitters are indeed okay. Condition 1 of the theorem follows from the next claim. Sn is equal to an times an minus 1 all the way down to a1. To prove this, consider the effect of all the at's on the rows of the identity matrix. For each t from 0 to n, and each binary coordinate x inside z mod 2z to the n, let ct to be the collection of binary coordinates y that agree with x after the tth digit. Then it is clear that the size of ctx must be 2 to the t. Now an induction shows that after applying at times at minus 1 all the way down to a1 to the identity matrix, the row indexed by x is the uniform probability vector concentrated on the digits labeled by the elements of ctx. That means it is equal to 1 over 2 to the t times the vector with 1 on the entries labeled by the coordinates y inside ctx. The detail of this induction can be seen on the screen, and interested viewers can pause and read. Now it remains to prove the minimality of this balancer construction. Suppose we have another decomposition of length k. We want to show that this is at least longer than the one we proposed. Suppose Sn is equal to fk times fk minus 1 all the way down to f1, where each fl is some Eij. We set ml to be the else truncation, fl times fl minus 1 all the way down to f1. Particularly, m0 is equal to in. Because each Eij is row stochastic, every row of every ml is a probability vector. For a probability vector p equal to p1 all the way to p capital N, we let hp be the Shannon entropy, defined by negative sum from 1 to capital N of Pm times log 2 of Pm. Taking the sum of the entropy of all the rows, we can define the total row entropy of ML, which we denote capital Phi. Now, a direct computation shows us that capital Phi of Mk is equal to capital N times N. Now, since going from each ML to ML plus 1, we're simply multiplying by some Eij, it makes sense to study how multiplying Eij will affect our entropy. We shall leave the bounding of the Shannon entropy on the screen, and claim that if ml and ml plus 1 differ in rows I and j, say those rows are given by vectors p and q, then the difference between the entropy of ml plus 1 and ml is 2 times h of p plus 2 over 2 minus hp minus h2, which is at most 2. This means each factor fl increases the entropy by at most 2, and we obtain that 2k is greater than or equal to N times n, which implies that k is greater than or equal to n times 2 to the n minus 1, as required. Now to finish this section, let us look at a 8-lane belt balancer that uses exactly 12 splitters, which is the minimal number that we have proven. Section 1.5. Constructing m-lane balancers for arbitrary m. A keen-eyed viewer might have noticed that in the previous section we skipped introducing the 3-lane balancer. One might also wonder how an m-lane balancer is built for an arbitrary m. Construction 1.10. A 3-lane balancer can be constructed as follows. First, build a 4-lane balancer, then connect the 4th output to the 4th input. Let us prove the validity of construction 1.10. To do so, we shall simply provide the construction and validity of an m-lane balancer. Construction 1.11. An m-lane belt balancer can be constructed as follows. First, build a 2 to the n lane balancer for any 2 to the n greater than or equal to m. Then connect the last r equal to 2 to the n minus m outputs to the last r inputs. Theorem 1.12. Let m be greater than or equal to 1, and let capital N be equal to 2 to the m be greater than or equal to m. Set r equal to n minus m, and partition the matrix as n into these blocks. Given an external input vector of size m, define the internal vector u of size r by the following feedback equation. U is equal to cx plus du. Then this equation has a unique solution, and the resulting external output, y equal to ax plus bu, satisfies y equal to sm times x. Proof. We first solve the feedback equation u equal to cx plus du, or equivalently, ir minus d times u is equal to cx. Note that d has rank 1, and has only one eigenvalue r over n. Since r is less than n, we have r over n is less than 1, so I minus d is invertible. Therefore, the feedback equation has a unique solution, u equal to I minus d inverse times c times x. Therefore, the effective external map is a plus b times I minus d inverse times c. A quick computation shows that T is a m by m matrix filled with 1 over n plus r over nm. Since n is equal to m plus r, we conclude 1 over n plus r over nm is equal to 1 over m. Therefore, T is indeed Sm, as required. Here is a 3-lane balancer. Do you see how this is constructed according to construction 1.10? Can you make your own balancer using construction 1.11? Before we move on to the final discussion, we would like to mention that the material of this video can be found in the form of a handbook titled Mathematics of Factorio, tentative title, given below in the description of this video. This also includes additional discussions on balancers with different colored belts, as well as splitters with priority settings. Now we welcome Bedfoot to present the final discussion on balancers to end this video.
(1.7) Balancers. Do we really need them? Although the use of balancers appears in many intermediate levels of factories, we remind the viewers that in practice, a well-designed factory should not require balancers in the following sense. Consider a collection of blue conveyor belts which transports 45 items per second each. if at all times as the factory is running, the belts are fully loaded with 45 items per second, then there is no need to balance, as we always have y equals 45 times the item for all I. At this point, one cannot add more to the belts. Only at the end of the belt, where items are consumed, would they become not fully loaded, in which case balancing is also not necessary. The above observation implies that balancing is only required if some of the belts are not at full capacity. If a belt is being loaded with an unknown number of items per second lower than full capacity, then we do not even know the number of items this belt should handle. So each belt may need to receive a range from 0 to the maximum amount of items, in which case a balancer may average out the inputs. But in a well-designed factory, the amount that a belt is transporting is always computable or can be estimated, allowing one to load a series of belts equally by design. Without a strict and disciplined building doctrine, one may find it difficult to construct a factory with such ideal belts, and to go a step further, may not want to. This is a game after all, and consideration of the optimal, the most efficient, the most perfect is not a requirement for enjoying said game. In that case, belt balancers are incredibly useful. We have a variety of sources for a particular item, and these manifest into a series of unevenly loaded belts, which causes imbalances from time to time, and belt balancers are a quick and easy solution to that. The object of this video is not to prohibit, maybe not the video, maybe this section, maybe it's me. The object of me is not to prohibit the use of belt balancers. I'm merely encouraging the viewer to think about what could have been improved at a technical level before using a balancer and potential issues it may cause, as follows. 1. As mentioned above, the perfect factory design does not require balancers. Such a perfect factory directs the precise exact number of ingredients to each process in the factory, and if one has spent considerable time and effort calculating and directing all these flows such that they deliver an exact amount of ingredients, then a balancer might disrupt this process. 2. Placing down a belt balancer may obscure throughput problems that the factory is experiencing. There may be a systemic problem with the factory, and that is what is causing the belts to not be loaded evenly, and a belt balancer can hide this information. Instead of us investigating how and why the flows are not even, a balancer tends to cause one to ignore the problem, and we might be unable to fix the problem at a later time. With these issues in mind, we believe, maybe more accurately I believe, that relying on the benefits of balancers will lead one to a place where the perfect factory is almost unobtainable. One may end up with a factory where, in order to achieve higher scale, the balancer must scale at the same time, embedding bad design into your particular factory building doctrine and obscuring what good design actually is. But you know what? Hey, this is just my opinion. I am not here to determine your fun. We can play this game any way we like, inefficiently, imperfectly, whatever we want. The path to the finish line isn't necessarily straight, but I am here to determine my fun. So fuck your balancers.